Hi, hello guys. It's a further continuation of symmetrical faults. These problems are very actually this is problems where actually the examination do what is so called a throw in of its weight to some of its own analytic problems. They need a serious practice, and you won't understand these problems if you are still using that system of being a student to say, hey, now you know what's about van Strayer, I prefer calculations, hey, theory makes me mad. Then how will you reason without theory with if you have to approach that particular problem or calculation then? And this is the problem that makes me fed up, because a student called me early in the morning around 4 o'clock, Mr. Akisana. Ke mametse listening to what? Harempe motho, mpatlele motho or what. All of a sudden, yes, I call, hey, many years, I really got, hey, bana, stop calling me in the morning. Ke mamela manane wa sirasa batho ba baholo bo re qoba bosiu. But anyway, let's do this problem. Basotho will tell you hore dia yanyisa. But let's approach it. It says a small generating station. It's a small generating station. Yeah. A small generating station has two alternators. 3000 kVA, 4000 or 4.5, 4500 kVA, and percentage reactance of 7% and 8% respectively. Okay, right. Oh, let's finish first. The circuit breakers have a rupturing capacity of 550 MVA. It is desired, that's very important, it is desired to extend the system by supply from the grid via a transformer of 750 kVA, via a transformer, let's say transformer. Is it a transformer? I think I've seen a transformer. It is desired to supply the system from the grid via a transformer of 7,500 kVA and 7.5% reactance. Find the reactance. Find the reactance of the reactor connected in the bus bar section to prevent the circuit breakers being overloaded. If a symmetrical short, very important, if a symmetrical short circuit occurs on the outgoing feeder connected to it, on the outgoing feeder connected to that particular reactor. Let's draw. We've got two alternators. Like this. And they are connected together. And each one is 3000 kVA. The other one is 4500 kVA. And it has what? This one is 7%, they say respectively. This one is 7%, this one is 8% respectively. The circuit breakers have a rupturing capacity. We did circuit breakers at the university. We did circuit breakers. This 150 MVA, it is the maximum short circuit fault that the circuit breakers should withstand. It means those circuit breakers are rated to interrupt a fault of 150 NVA, not more than that. Very, very important. Very, very, very important. Now we see why Mr. Tulano was so desperate for a call while studying. All right. It is desired to extend the system by supply from the grid via a transformer of 750 kVA. Let's write it. Okay, let's put this 8% there. Okay, let's do this. This is 4,500 kVA, and then this is 8%. It belongs there. These are alternators. And then let's put to this grid. A grid is a connection of component connected together to supply power to a power system. That's it. That's the grid. So it is connected. This is a grid. They should be connected to this transformer of 7,500 kVA, and it has a percentage of 7.5%. But how is it connected to this? Listen to this one. It is connected reactance. Find the reactance of the reactor connected in the bus bar. Here, in the bus bar. There we go. In the bus bar section to prevent the circuit being overloaded. If a symmetrical fault, something like this. If a symmetrical short circuit occurs on an outgoing feeder connected to that reactor, this is where the fault occurs. The symmetrical fault is gonna occur on this outgoing line. It's a line or a feeder, and that feeder is connected to the reactor that link this transformer to these two alternators. One additional information. You remember yesterday we showed that you can connect a reactor in series with the generator, and they can also be connected in the feeders or in the bus bar. And I said in practice it's not. It is in actual practice. Normally they don't connect reactors in series with reactors for two particular reasons. It has sufficient internal reactance to protect itself from short circuit. Secondly, and this is very, very important, the reactors in series with the generators, or the reactors connected, for instance, in the feeders like this, they are not good. Why? Because even normal operation, there is a constant voltage drop and power loss. For that reason in particular, the reactors are normally connected in the bus bars. They are located in the bus bars because here and in the lines there is a constant power loss and voltage drop. That's why normally we put reactors there to link this. In practice or at the mines, normally they've got bus bar sections. Let's say this bus bar, they can put it can be something, it can have a bus bar section. It is kept open such that this one can only supply this line. Only one line is supplied by one generator. And then if there is a fault here, for instance, if there is a fault here, this bus bar section at the mine, they close it, and then if everything is still fine here, and this alternator generator, if it's a generator, it can continue and supply power to other lines. Or if there's a problem at all here, this is called a ring system, and its main advantage is that problems are localized. If there's a problem here, if like a fault there can't be this fault here can't affect the conditions, healthy conditions in here. This generator will continue to supply, but you will see probably, I think someone there are two problems left for maybe next week. There's a tie bar system. You're gonna see what the problem is when we use tie bar, but it has more advantages than this. But at the moment we prefer this because it is used to localize problems or faults. That's why normally they prefer this one. Right, now we've got this and this one we don't have. We can call it X. Let me draw actually what is required here, and then okay, there were two alternators. Each alternator feed one line, and then one line was added in order to the reactor was added to link this transformer to this power system. And then we were told that there is a line connected to the reactors and the fault occurs on it. Basically, this is what is needed from you. This is the line diagram of this information there. That's basically what is needed, and it's marks. It's what is needed. The DMR want to see this at your station or power substation when they come for this particular information. They want to see this on the when they enter on the wall. There must be this. Right. Basically, this is the case. Now we can calculate. Which one is the biggest? Is this one. I'm gonna choose this one to be my base. I'm gonna choose a base of 7,500 kVA. Why? For me, it is the largest ratings of the three, so I choose this one specifically. That's why I chose this one. You can choose this one, you can choose this one, but we will still get the same answer. But I prefer the largest. So I chose this. I choose this one. That's number one. Now let's calculate for this one. We have what? We have let's say alternate percentage X, say A, this one is equals to 7,500, this one, divide by the rating, multiply by 7. Why? We convert the percentage reactance of different equipment to the same base value. That's basically what we are doing here with regard to these calculations. And it is equals to what? It is equals to 7,500 divided by 3,000 multiply by 7. 17.5. This is 17.5%. It is for this one. We come to this one. It is the percentage XB, which is 7,500 divided by 4,500 multiplied by 8 is equals to what? It's equals to 7,500 divided by 4,500 multiplied by 8 is equals to 13.33%. All right, and then this one is 7 divided by 7 multiplied. This one percentage XC. This one is equals to 7.5%. Why? Is 7,500 divided by 7,500 is 1. Multiply by 7.5. You'll get that one. Now let's draw the percentage. We've got something like this. This is the neutral, and then it is this one, and then they were together, and then we've got this one. It is that one. There's a fault on it there, and then we've got this one linked to it. It's something like this. So we've got what? We've got 17.5 and then 13.33 and then 7.5%. These are percentages, and then we have to find the fault there. This is a point. This is a point. And remember, when you think of a point in an electrical circuit, you think of the parallel branch. But we'll come to that one. This one is in parallel to this one. They're gonna form one circuit. But I need space, guys. I need space. I need space. What I know, we are calculating this one. We are calculating this one. We'll remember, and then we've got 150. Okay. Oh, okay, I still got information here in my hand. Okay, let me not delete it all. Okay, right. This one is in parallel with this one. So it's gonna be percentage X AB. AB is equal to, say, 17.5 multiplied by 13.33 divided by 17.5 plus 13.33 is equal to 17.5 multiplied by 13.33. Answer divided by open brackets 17.5 plus 13.33 is equal to what? Is equal to 7.557%. This is the percentage reactance of this parallel branch, this one. Now we've got something like what? Now we've got something like, this is our neutral, something like this. We've got a point there where the fault occurs there, and then we've got a reactance which is in series with it, which link this transformer to the others. So we've got what? We've got 7.5, and then this one is the percentage X. We have assumed it to be X because it has to be calculated. And we are not calculating the percentage reactance. We are calculating the reactance. All right. All right, Van Strayer. All right, Van Strayer. All right, Van Strayer. And we have assumed a bus bar voltage of 3,300. Okay. Okay, okay. All right. Now, what's the plan? This one is in parallel with this. This one, they are in series. They are added together. But they are in parallel with this one. And this one is now what? It's 7.57%. There. You're gonna have a very, very long night here. Let's continue, gentlemen. 150 MVA. Okay, it's fine. 150 MVA. Right. So let's take the parallel combination of this. Percentage XT, total percentage reactance, is gonna be 7.57. This one multiply by open brackets. This one's together is 7.5 plus percentage X. Why we add them? They are in series. We add them together. We add them together because they are in series. All over 7.57 plus 7.5 plus percentage X. This is one thing there. Now let's check. Let's check. So let's check. Let's check. Let's do this actually, man. Let's do this. It is 7.57 multiplied by 7.5. Answer. We've got 56. 56.77, 56.775 multiply by, oh, this one again multiply by that one is plus 7.57 percentage x. Our simple a high school that primary actual. And then this one 7.57 plus 7.5 plus percentage x. I've just removed the brackets there, and then it's equal to what? Let's check. 56.77 there plus 7.57 percentage x all over this one plus that one, this one plus that one is equal to what? It's 7.57 plus 7.5. Answer is 15.07 plus percentage x. I've just added the like terms there. Ne? Right, is equals to our percentage x total. Our percentage x total. Right. But remember, this reactance of the total system should be able to interrupt a fault of 150. Or let's do this. Now then that we've got this, the percentage reactance, we know that the short circuit MVA is equals to the base KVA. The selected one, I think it's 7,500, yes, multiply by 100 over percentage XT. And what is percentage XT? We are going there. So this, the short circuit MVA is given as 150 multiplied by 10 to the power 3 kVA. Why? I want to use kVA now because my base here is 7,500 kVA. We must have the same basic units. Multiply by 100 over percentage reactance, and it is equal to what? It's equals to 56.77 plus 7.5 percentage x all over 15.07 plus percentage x. It's all right, man. Let's enjoy this, gentlemen. We are back to grade 1, where we used to do fractions. Let's check right away. Let's divide by this. This side. It will be 150 exponent 3 divided by 7,500 is equals to 20. kVA, it cancels kVA. We are only left with 20. Let's write it here. 20 is equals to what? We are left with that. Let's write it down. Divide by 56. Oh, okay. Let's do this. We are left with that. Then we've got 100 multiply by, this is a fraction over fraction. Let's swap it. But when we swap it, we do what? We multiply. You still remember you used to have 7 over 7 divided by 6. This is equals to 7 multiplied by 6 over 7. We are used to this. So this is 15.07 plus percentage x all over all over 56,77 plus 7.5 percentage x. All right. We can divide by 100 here. Let's divide by 100. 20 divided by 100 is equals to what? 0,2 is equals to 15,07 plus percentage x all over 56,77 plus 7.5 percentage x. You see, Mr. Akisanang, why I hate these problems. I don't have space. And people say, hey, he's running away from those problems. No, not at all. Not at all. Now I can erase this. Let's erase it all together. I've got information on, I've got a question on my hand, in my hand, so I can erase that. So this is the situation. We can cross multiply there. We can say 0,2 is equals to, let's cross multiply. Open brackets, 56,77 plus 7,5 percentage x is equals to what? Is equals to 15,07 plus percentage x. All right, let's multiply through. Let's multiply through. 0.2 multiplied by 56,77 is equals to 11,354. 0.2 multiplied by 56,77. Yes, plus 0.2 multiplied by 7,5. It's 1,5 percentage x. Is percentage x is equals to what? 15,07 plus percentage x. All right, van Strayer, we can bring this ones this side. It's gonna be what? 11,354 minus this one. Actually, I'm just grouping like terms, gentlemen. Minus 15,07. Answer, it's minus 3,716 is equals to, this one can go that side. Because of it goes that side, it changes a sign as well. It's gonna be minus. So it's gonna be 1.5 minus 1 is gonna be minus 0.5. 1.5 minus just 1 percentage x. All right, we can therefore percentage x is equals to what? We just want to make subject of the formula. Let's say negative by negative is positive. Okay, so it's 3,716 divided by 0.5. Answer, it's 7,432%. But remember, this is the percentage of that particular reactor on the line diagram. This now remember, percentage x reactance is equals to the S base over VB squared multiply by x. You are requested to calculate this. Multiply by 100%. We're gonna divide by this in order to cancel the percentage. It's gonna be a point of interest, this guys. Actually, I argued earlier with 1%. This formula, it must include 100% to show that this percentage reactance has been expressed in the form of percentage. So to get rid of this percentage, we must divide by that one. We must divide by that 100. We've got 7,432 divided by 100. And I'm still going to emphasize that again. And I'm going to tell you why. It's equals to, this is equal to 7,500. Yes. as a base over, I think it was 3,300. Let's convert it to kilovolts. It's 3.3 squared multiplied by x. That's how I see it. Let's see. 7.432 divided by 100. It's so much. Let's cross multiply. 0.07432 multiplied by 3.3 squared. It's 0.809. Let's divide by 7,500. Answer. And I'm gonna maintain that, guys. I'm gonna maintain that the reactance of this, in my view, is equal to 0.00179 ohms. Those people got 0.0105 ohms. Why? Because they, in this formula, they didn't include 100. They didn't include 100. This formula must have 100. If you remove this 100, you're gonna get this. But this formula, I can't remember, but the logic is, if this thing is percentage, how you gonna get rid of percentage? You have to divide by this 100 to get rid of percentage. How you gonna do that? But let's leave it that, guys. In my view, this is the correct answer. This is the correct answer. I've included 100 to get rid of the percentage. Hey guys, please subscribe, like the video, send one problem via an email. If you got my numbers, call and ask me to do something. I can only do problems if someone sent. But thank you very much for watching. I'm gonna see you in the next video. Mwah. Shora.